In this session, we will discuss about the basic concepts of probability. When we are going to discuss about probability, first we have to have an idea regarding the terms which are commonly used in probability. When we are going to discuss about the concepts of probability, there are some scientific terms actually we have to use. First, we will have a look on those terms, and then when we are discussing along with these explanation for these terms, we will discuss about some theories and some concepts which are generally used in the field of probability. When we are going to discuss about probability, first we have to have an idea about what is meant by an experiment. An experiment is supposed to be a mechanism whose outcome is uncertain or cannot be predictable. It is simply we can say it in this way. Now think about if you are tossing a coin. If you are tossing a coin, then a coin has two sides, head and tail. Once you flip or once you toss the coin, none of us can say that exactly we are getting head at this time, or no one can say that we are exactly getting tail. The only thing we know is we know that we are getting either head or tail, but none of us can exactly say that we are getting either head or we are getting the tail. Therefore, that is why it is saying that experiment is a mechanism. Here, the mechanism is we are flipping the coin or tossing the coin. Then whose outcome is uncertain. Now we can say that this is the outcome. We know it is either head or either tail. There is uncertainty. It is because we cannot say that exactly we are getting head or exactly we are getting tail. Therefore, here we can see that outcome is uncertainty or cannot be predictable. The only thing is we know that we will get one of these, whether it is head or tail, but we cannot exactly say that we are getting exactly head or exactly tail. Therefore, such mechanism is supposed to be an experiment. If I consider another example on this, suppose that you are rolling a die, which is numbered from 1 to 6. Once you roll a balanced die, we'll suppose it is a balanced die, numbered from 1 to 6, and if you are observing the number got on the surface of the die, at that time also, what we can comment is we know that exactly we are getting a number. It is out of these 6 numbers, whether it is 1, it can be 2, it can be 3, it can be 4, 5, or 6. But none of us can say that exactly we are getting 1 at this time, exactly getting 2 at this time. Likewise, we cannot comment. The only thing is we just know what are the possible outcomes, and none of us can say that the exact outcome once you are performing this considered trial of that experiment. Now we will move on to the next term, which is generally used in probability. It is sample space. Sample space is meant to be all possible outcomes of the experiment. If you are considering all the possible outcomes of a given an experiment, then the set of outcomes is supposed to be the sample space for that experiment. We are generally denoted this sample space using the uppercase English letter S. We are using uppercase letter S to denote the sample space. Since according to this explanation of this sample space, then we know that S is said to be the sample space of the experiment. Then we know that if you are considering the experiment of flipping a coin, then we know that sample space is either getting a head or either getting a tail. Then this would be the sample space for the first experiment. If you are considering the second experiment, it is the rolling a die, then we know that the sample space will be the numbers from 1 to 6. It is because we know that we are getting either one of these 6 numbers. Therefore, we can say that sample space is equal to 1, 2, 3, 4, 5, and 6. This is how we are defining the sample space. And then we will move for the next term. It is event. So far we have discussed about experiment and sample space. Based on sample space, if you are identifying any subset from the sample space, then such is called to be an event of the experiment. Therefore, if you are considering any subset from the sample space, then it is supposed to be an event of the considered experiment. Generally, an event is denoted using uppercase English letters, but we are not using the uppercase letter S. It is because it is already allocated for the sample space. Apart from this letter S, we can use all other letters to denote an event. Therefore, we can simply say, we can say event as event A, event B, event C. Likewise, we can say that event P, event Q may be there, then or else event X, event Y, event Z. Likewise, there may be events. We can name these events using the uppercase English letters. If I consider about the one possible event from the first experiment, it is the flipping a coin. Flipping a coin or tossing a coin. If you are considering the experiment of flipping or tossing a coin, then I can say that one event will be event of getting a head. Event of getting a head. And another can be said as another event can be event of getting a tail. Likewise, we can identify two events for the first experiment. Another one can say that event of getting either head or tail. Another one can say such as an event. Maybe C, maybe event of getting head or tail. This can be again another event, but it is actually a combination of these two events. Here we can just say these are simple events, but once this is considered, this cannot be considered as a simple event. It is because it is actually a combination of these two events. Therefore, if we are in events in this case, we will have different concepts. We can apply them if you need to identify the probabilities based on this type of compound events. If you consider about the second experiment of rolling a die, then we have identified, if you are considering an experiment for rolling a die, then we have identified that S is equal, it is from 1 to 6. It is from 1 to 6. And if I consider about simple event, let A be event of getting 1. Getting 1 on the surface. This is one event that we can consider. Likewise, event B can be considered as event of getting 2 on the surface. Likewise, you can name the events. And if I take another event as X, I am saying that event of getting an odd number on the surface. Likewise, we can identify the events. When we are defining the events for each event, we can identify the elements for the considered events. Therefore, event of getting 1, here since it is simple, we will say that A is equal to 1. Then if you are considering the event of X, event of getting an odd number on the surface. Therefore, the odd numbers that we can get is 1, 3, and 5. Then the elements of the set X is said to be 1, 3, and 5. Anyhow, what we have to Follow the rule is we have to use the uppercase English letters to denote an event. I have already discussed about this simple event. A simple event is considered as an event consisting of a single outcome. Here we can see that here we are having a single outcome, but this cannot be considered as single outcome. It is because there is a combination of outcomes. We may get a 1, we may get 3, we may get 5. Therefore, if it is a simple event, then we can see that there is a single outcome in the what we are considered as the event. So far, when we are discussing about the events, we have just discussed about the single events only. It means only one event. Now we will pay the attention on what will happen if you are considering any two events for a given experiment. Suppose that A and B are any two events for a defined experiment. Now, based on these two defined events, now we will identify what is said to be mutually exclusive event. Suppose that you are performing an experiment and you are having an experiment having two events or two possible outcomes. Then the occurrence of one event prevents the occurrence of the other event. Then such events are said to be mutually exclusive events. And simply, if you are considering the experiment of tossing a coin, if you are considering the experiment of tossing a coin, if you are let A is event of getting head, then event B I am saying as getting tail. If you are considering about the experiment of tossing a coin, if you are considering in that experiment, if you are considering about getting a head, what we can see here is getting a head. If you are getting a head, then it prevents the happening of the next event. It means that at the same time you cannot get head and you cannot get a tail. It means that you can either get a head or you can either get a tail. Likewise, we have to consider these two events. Therefore, if such scenario occurs, then we can say that those two events are mutually exclusive events. If I consider another example on this, now think about the next experiment I am taking here is rolling a die. If I am considering an experiment of rolling a die, what we can consider here is, if I am considering two events as one event is named as P, getting an odd number. Event Q is, I'm saying it as getting an even number. Therefore, if you are considering these two events, now event P having the elements as 1, 3, and 5. Event Q have the elements 2, 4, and 6. It is first set of elements are supposed to be odd numbers, and the elements for the event Q are supposed to be the even numbers. Now, if you consider about these two events, you can see that there are no any common elements. It means that occurrence of this event has prevented the occurrence of the next event. Simply, rather than considering about the common events, it would be simply we can consider this as occurrence of one event prevents the occurrence of next event. And simply, the both events cannot be occur at the same time. Therefore, in such situation, we can say that P and Q are mutually exclusive events. Therefore, now since we can see that there is no any common elements as well, therefore we can say that P and Q are mutually exclusive event. If two events are said to be mutually exclusive, then we can see this equality as well. If you are consider the notation of A intersection of B, A intersection of B, this would be equal to a what if we are saying as the null set. It means that here also we can see that there is no any common elements. That's why the intersection of these two events gives us the null set. Therefore, if you are considering the event in this way, A intersect B, then if you are writing down the elements used in the set, we will have it as an empty set. Therefore, if you are considering any two mutually exclusive events, then we will get A intersect. The probability of A intersect will be equal to 0. This is for the mutually exclusive events. For in simply we can say that if two events are said to be mutually exclusive, then there is no any common elements. Therefore, the probability of A intersect B is equal to 0 if A and B are two mutually exclusive events. We can extend this concept more than two events as well. It is not limited only for two events. It can be expanded for more than two events as well. Now we will move for the next one. Next type of events, it is exhaustive events. When we are consider a single experiment, yeah, suppose that if there are two events named as A and B, as if those two events are said to be exhaustive, if it's certain that at least one of them occurs. It is quite in this way. Consider about flipping a coin. If you are considering this example, what you know is you are getting either head, you are getting either tail. Therefore, if you are using a Venn diagram, now you can see that one part you are getting head, another part you are getting tail. Therefore, now you can see that this getting head and getting tail, those two events completes the sample space. It is quite in this way. If you write down the sample space for this experiment, you can see that there are only two possible outcomes. Now you have identified two events as that as well. Therefore, we can say that those two events are said to be exhaustive events. It means that simply if a set of events are said to be exhaustive, then exhaustive if the set of events completes the sample space. If you are considering any set of exhaustive events, there cannot be any other events than the considered set of events. It can be on that is why we can say that if two events are exhaustive event, then at least one of them must occur. The next thing is equally likely events. If we are having two or more events which are having the same chance of being occurred, then such events are said to be the equally likely events. When we discuss about this equally likely events, then it has said that two or more events are said to be equally like if the chance of their happening is equal. Consider about if you are considering the same experiment, flipping a coin. If you suppose that you are having a balanced coin, suppose that you are having a balanced coin. Now, if you observe this coin, you can see that there are two sides and each side has an equal chance. It is because since it is a balanced coin, we are having an equal chance of getting head and equal chance of getting tail. Therefore, if you are considering event A as getting head and event B considered as getting tail. Then we can say that these two events are equally likely events. It is because now, since the coin is a balanced coin, we have identified that there is the same chance of getting head as well as getting tail. That is why we have identified that these two events are supposed to be two equally likely events. And if you are considering another example as the rolling a die, I am using these two examples. It is because the things can be easily explained and easily understood using these simple examples. That's why. But there can be so many other. There can be various examples we can take on the explanation of these matters. Now, if you are considering rolling a die, then if you are considering these events, A is obtain 1 on the surface. Likewise, obtain 2. Event B, I am saying event C is obtain 3 on the surface. Event D, obtain 4 on the surface. Event E, supposed to be obtain 5 on the surface. Event F, I am saying obtain 6 on the surface. If you consider that the die which you have rolled is a balanced die, then we can see that there is a equal chance of getting A or the getting 1, getting 2, getting 3, getting 4, 5 and 6. Therefore, we can consider that these 6 events are equally likely events. And if you are considering another way, if X is supposed to be getting an odd number, and event Y is supposed to be getting an even number. If you are having these two events, in the first event you are having the elements as 1, 3 and 5. In the next event you are having the elements as 2, 4 and 6. Now you can see that same number of elements implies that laterally we will discuss this concept. Here we are having equal number of elements. Therefore, since it is a balanced die, we can say that the chance of occurrence of event X is same as the chance of occurrence of event Y. That is, then we can say that event X and event Y are said to be equally likely events. Then we will move for the next concept. Here we will discuss about the independence of events. When we are discussing about the independence of events, we will consider this for two events, but it can be also considered more than for two events as well. If you are considering the independence of two events, it simply we can say it as the occurrence of one event does not depends on or does not affects on the occurrence of another event, then such events are said to be the independent events. In simply, if you are considering an experiment of rolling a die, okay, I will consider another example. I will consider I'm considering an event of getting heavy rain. We will say event A as getting heavy rains. Event of getting heavy rains. To Sri Lanka. And I am considering another event as getting floods in USA. If you are considering these two events, getting heavy rains to Sri Lanka has not affected on getting floods in USA or vice versa. It means that getting floods in USA does not affect with the getting heavy rains to Sri Lanka. Therefore, if you are considering these two events, then this can be considered as independent event. It is because occurrence of one event does not affect on the occurrence of the next event. If you are considering these two concepts, mutual exclusive and independent events, these are not same concepts. In the mutually exclusive, what we have discussed was the occurrence of one event prevents the occurrence of next event. It means that if you are considering two events, then those events cannot be happened at the same time. But if you are considering the independence of two events, then both of these events can be happen at the same time, but occurrence of one event has not affected on the occurrence of next event. That is the difference between these two concepts. Therefore, we can simply say that the occurrence of one event does not affect on the occurrence of next event, then such two events are said to be independent events. The next concept that we have to discuss is the dependent event. Then the negation of this independent can be considered as a dependent event. Therefore, we can simply say that the occurrence of one event affects on the occurrence of next event. Then we will say such two events as dependent events. If you are considering example in this form, the two events in this way. Now we will consider getting floods in Sri Lanka. If we are getting heavy rains to Sri Lanka and if we are having getting floods in Sri Lanka, then what we can see is there is a dependence. It is because if we are getting heavy rains to Sri Lanka, then there is a chance of getting floods in Sri Lanka as well. Therefore, getting floods is affected by this getting heavy rains to Sri Lanka. Therefore, event B is affected on affected by event A. Now, suppose that if it is a dry season and it is simply in this way. If you are not getting heavy rains, or if you are not getting rains, or if it is totally a if you are experiencing with the dry climate, then we may not able to see these floods. It is because getting floods is directly affected by this getting heavy rains to Sri Lanka. Therefore, such two events can be considered as examples for dependent events. Now we will discuss, or we will move for the next concept. This is one of the most important thing actually we have to discuss in this chapter. We will consider about the probability of an event. So far we have discussed about the things related to what is an experiment, how to define the sample space, and we have identified an event. Then when we are discussing on the events, we have discussed several types of events that we can see in the concepts of probability. We have discussed mutually exclusive events, we have discussed about exhaustive events, equally likely events, and the dependence of two events as well as the independence of two events. Now we will see how we can define the probability of an event. When we are going to discuss or define the probability of an event, there are several ways that we can define the probability of an event. In here, I will discuss about the classical approach for defining the probability. If you are saying this as the classical probability, we can define the probability of an event as follows. Suppose that we have performed or we have conducted an experiment having the sample space as is having finitely many elements. It means that if you are conducting an experiment, then once you observe your sample space, it should have finitely many elements. There may be many elements, but it should be a finite number of elements. And if it is equally like to occur, then we can say for any event lettered as E, then probability of the considered event E can be denoted as PE. If you are having an event E, then we can say that probability of event E. It is denoted in this way, probability of event E. And then this can be defined as probability of event E can be defined as number of elements in the considered event, and it has to be divided by the number of elements in the sample space. I have used the notations here, but once you see this explanation, you can see how it has defined. Probability of the event has defined as number of elements in set E divided by number of elements in set S, where S is defined as the sample space and E is defined as the event. This is said to be the classical probability. Therefore, using the definition for classical probability, you can obtain this equation. If you are having an event E, then the probability of the event E can be obtained as number of elements in event E divided by the number of elements in the sample space. When we are discussing about the probability of an event, once we discuss about the axiomatic approach of the probability, there are some rules. Actually, mainly we will discuss 5 rules, but apart from that, if you have a general idea regarding the probability of an event, once you perform this calculation using the numeric value, if you are performing the calculation, you may get a numeric value for the probability of any given event. I will use the same letter E. If you are considering the probability of a given event E, then this should be definitely lies in between 0 and 1, inclusively 0 and 1. It means that the minimum value that we can obtain for any probability of an event is 0, and the maximum probability that we can assign for or obtain for any event is 1. Otherwise, we will get a value for the probability of an event which is in between 0 and 1. Therefore, this is one major rule that we have to follow when we are dealing with the probability values. Here I have included 3 examples to have an idea regarding the value that we can obtain for probability. In here, I told that probability of an event must be lies in between 0 and 1, inclusively 0 and 1. Now we'll see what is actually defined when the probability equals 0 and probability equals 1, and a value in between these two values 0 and 1. If you know that the event cannot be happen ever, then the probability of such an event is equal to 0. As a simple example, a human being living without blood, or the probability or the chance of a human being living without blood should be equal to 0. It is because we know that living without blood is not a possible event. That is why we can say that probability of such event is equal to 0. It means that probability of man living without blood is equal to 0. If you are considering another example, the sun rising from west, we know that sun rising from west cannot be happen ever for a country like Sri Lanka, and generally it is a common thing that we can see. If you are considering sun rising from west, if you are considering the event of sun rising from west, that event cannot be happen ever. Therefore, we can say that the chance or the probability of that event is equal to 0. Since we know that the event cannot be happen ever exactly, we have to assign the probability of such an event as 0. If you know that, in the next case, if you know that the event that you are consider is exactly happens, then probability of such event is 0. The sun rising from east. If you are considering the event of sun rising from east, then we know that the event of sun rising from east is exactly happens. That is why we are saying that probability of that event is equal to 1. Here another example is included. The probability of human's death is 1. If you born, then we know that there is definitely a death for all of us. But the only thing we cannot predict is when is that. But we all know that if we born, then there is a death for all of us. Therefore, we can see that we can say that the probability of humans death is 1. There is no any person who cannot just living eternally. It means that that person has to be faced with the event of getting a death. And if you consider the next type of the numerical values that we can get in for this probability is it is just the values in between 0 and 1. It means that if you are not experiencing one of the first two events, then you must have a probability value which is in between 0 and 1. It is simply like this. If you elaborate this inequality, then we can actually divide this into 3 parts. It is the first part is probability of this event equals 0, and then probability of this event equals 1. This or the next case is probability of this event less than 1 greater than 0. Now since we can see these two equalities, that is why we are including these two including these two events in this inequality by using this equal signs as well. If you are considering if it is apart from the initially mentioned two events, then the probability value should be definitely in between 0 and 1. That is why we can say as an example, if you are considering the probability of winning a lottery, we may get a win or we may get a lose. Therefore, we cannot exactly say that we are getting exactly a win, we are getting exactly a lose. We cannot say it in that way. The only thing is there is a chance of getting a winning or there is a chance of getting a loss as well. That is why we can say that probability of such an event should be definitely lies in between 0 and 1. Now we will discuss about another concept used in probability, which is supposed to be named as probability tree. Actually, this probability tree is one method actually we are using in probability for the easiness of calculations. It is because once we show the experiment in a graphical way, then it will be really easy for us to identify the probabilities and identify what is the process of this experiment. Therefore, if you are considering any given experiment, then if you're supposed to visualize this experiment, then we can use this probability tree and we can use these probability trees to calculate the probability values easily. I will use an example and show you how we can use this probability tree to identify the sample space, to calculate the values. Likewise, there are so many advantages of using this probability tree. Suppose that you are considering an experiment of tossing 3 coins simultaneously. You are tossing 3 coins simultaneously. It means that I will name this as to coin 1. You are having 3 coins. Here it is coin 2, another coin 3. If you see about the outcomes of this or the sample space for these 3, for the coin 1, you can see that you are getting either head or tail. Coin 2, you are getting head or tail. Coin 3, you are getting head or tail. Now think that if you are tossing three coins, then we can visualize it using probability tree in the following way. Suppose that you are tossing the first coin. Tossing of the first coin gives you head or else it is a tail. This is for the coin 1. And at the end of now we can see that if you are going to create this as a tree diagram, therefore you can see that these are branches. At the end of each branch we have to name the outcome or the activity we have observed, and on these branches we have to mention down the probability value. Suppose that this is a balance coin, then probability of getting head is half, probability of getting tail is also half. Likewise, now coin 1 has finished. Now we have to consider this for coin 2. If once you get head from coin 1, then you can get another two outcomes from coin 2. The outcomes will be head and tail. And if you are considering this tail in here, then you are getting another heads or tails for this coin 2. Is for coin 2. For the coin 2 also, if it is suppose that it is same probabilities, then it will be half and half. Likewise, this is now for the coin 2. And if you are considering the coin 3 as well, it is coin 3. This should be head and this should be tail. Here also we are getting head and tail. Similarly, we are getting tail, head and tail. Now, if you suppose that coin 3 is also having the same chance of getting heads and tails, we can see that the probability is as half and half. Here also it is half and half. Likewise, we can assign the probability values as well. Now, if you see, actually this concept is supposed to be a tree diagram, and if you see at the end of this tree diagram, here this show all the possible outcomes. It means that if you are consider this is supposed to be a branch of a tree, likewise we can now see that there are 8 branches altogether. Now, if you go along with each branch, you can easily identify what are the possible outcomes of this experiment. Therefore, if you consider the first branch, you can see that here it is head with another 2 heads. Then you can see this as altogether there are 3 heads, then head, head and head. Then if you consider for the second branch, it can be going this way. Now, first coin head, second coin head, but in the third coin, it is a tail. Therefore, this is the next outcome that you can see. Likewise, we can say it as head, tail, and head, head, tail, and tail, head, tail, and tail. Then tail, head with head, head with tail, then tail, another tail with head, and in all 3 coins we are getting tails. Therefore, this has identified as the sample space, which is denoted as the uppercase letter S. Now you can see that the set of elements that we can consider for the sample space is included here. And using a tree diagram also, we can easily obtain the probability values as well. If you suppose the first branch, here you can see that if you are considering the first branch in this way, now you can see that there are 3 probability values. You have to take the product of these 3 probability values to identify the product of this event. It is half into half into half. This altogether 1/8. Then if you are considering the next event in this way, next branch can be now use another color to denote it. If I use the second branch, then it will be actually coming in this way, and now it has to go in this way. That then we can see that again half width, here it is half, then it is 1 over 8. Likewise, since we are having equal coins, this balance coin, we can get all these probabilities as 1 over 8. All are equally likely events. Therefore, to calculate the probability of an event, we have to get the product of the probability values of the considered branch. This is how we are using the probability tree or tree diagram for visualizing an experiment, as well as this will be helpful for the calculations as well. And now we will discuss for the relative frequency theory of probability. Suppose that you are repeating the same experiment for large number of times, then we can see that the relative frequency of the occurrence of the event approximates to the probability of that event. Actually, in the last session, we have discussed about this matter as well. We have not considered it as just the repeating an experiment for large number of time. And simply, we have defined it as the relative frequency as the probability of an event. But actually, it is coming based on this relative frequency theory. Suppose that you are conducting an experiment as the flipping a coin. If you are flipping a coin, suppose that you have flipped the coin for 100 times. Suppose that you have flipped the coin for 100 times, and you have obtained heads for 56. Out of this 100, you have obtained heads. You have obtained 56 heads. Therefore, if you are considering the event of getting probability of getting heads is equal to 56 divided by 100 is equal to 0.56. Suppose that you have again tossed this coin. Then if you have again tossed the coin, then this would be added with 1. Then this would become 101, since we are having an additional toss. Then in this case, what we can see is we are getting either head or we are getting either tail. In this way around, what we can see is if we are getting a head altogether, now here we had 56 heads. Now here we had 57. If it is obtained one head at this toss. But if you obtain tail at this moment, the number of heads will be still at the same number. It would be 56. Yeah, this is not, if you are getting a tail, then number of heads would not be changed. It is exactly 56 as it is, since we have obtained a tail there. In this situation, if you calculate the probability of getting a head, this would be equal to 57 divided by 101. It is because we have observed a head and we have altogether had 101 tosses. Then here also we are getting a value which is near to this 0.5634. In this situation, now you can see that the obtaining another head has not affected on this probability value much more. Since we have repeated the experiment for large number of time, this value has now gone for a limited value. And if you suppose that if you have obtained a tail here, and now we can see that in this situation, probability of getting head is now 56 divided by 101. If you perform this calculation, then you will get this value as 0.5544. Here also we can see that all these three values are nearly similar values, or quite similar, these three values. Therefore, we can see that since we have repeated the experiment for large number of times, the probability value has limited. Therefore, since it is limited to value, then such value is said to be the probability of that event. It is said to be the relative frequency theory of probability. And in the next part, there are axiomatic approach, the probability rules under axiomatic approach. And if you look on the basic probability rules under the axiomatic approach, so far we have discussed the things related with the classical probability, but if you consider about the rules under the axiomatic approach, this will be same as the definition obtained at the classical probability as well. If you go through these rules which have defined under axiomatic approach, if you suppose that event is given as A, then it is saying that probability of this event should be definitely less than or equal to 1 and greater than or equal to 0. And it says that the next rule is probability of sample space should be equal to 1. It is because in the probability of getting an event from sample space should be exactly 1. It is because we have defined the sample space as it is the set of all possible outcomes. Therefore, sample space must be happen ever. It is because since there is no any outcomes other than from this the elements in the sample space. The third rule, it has divided into two parts. In general, for any two events, then we can use this equality. For any two events, we can observe that probability of A union B is equal to probability of A plus, probability of B minus, probability of A intersect B. It means that if you are considering it using a Venn diagram, here you may have the two events, event A and event B. If you suppose that you need to get this probability of the A union B, you can have the A union B in this way. Now, if you see that how we can get the probability or this A union B, we can get it from by adding this part completely. Now it is go for A, and if you consider about the combining this with or coloring this with the event B, now you can see that there is one part which has already overlapped. It is because now in this part you can see that both colors are used. That is why one part of them has reduced. It is why we are having the subtraction as this P or the A intersect B. Here we can see that the subtraction is used here. It is now, if you combine this concept with probability, then it could be PA, probability of event A plus probability of event B minus probability of event A intersect B. This is for any two general events we are considering. What we are saying as if the events are not mutually exclusive or not mutually disjoint, we can use this equality. But if the events are two events, these two events are disjoint events, then we can identify that probability of A union B is equal to probability of A plus probability of B. It is because if you draw the Venn diagram for this, then you can see that these are two disjoint events, or we can simply say these are two mutually exclusive events. If you suppose that you need to get the A union B, then we get it from this, and we have to color the B as well. That is how we are getting the event A union B. Here we cannot see that there is any intersection. that value would be 0. That is what I have explained when I am what I have said when I'm explaining the mutually exclusive, and therefore now you can see that for mutually exclusive events we cannot see any in this intersection term. The probability of intersected part is 0 since there is no intersection included once the events are disjoint or mutually exclusive events. In the fourth one, suppose that A and B are two subsets, then we can say that probability of A is less than or equal to probability of B. In this wordings, it is given in the other way around. I will use the same way. Suppose that B is a subset of A. Suppose that B is a subset of A. Then this implies that probability of B is less than or equal probability of A. It is quite in this way. Now think that if you are having A is the outer one and B is the inner one. Now you can see that there are less number of elements will be in set B compared to set 1. That's why we are getting the probability of B less than probability of A. And since it is a subset, we can sometimes A itself being a subset of B, then the equality exists. It is because we can see that in some situations we are having subsets as A and B as well. The same will be another again considered as the subset as B. In this situation, the equality exists, but in this situation, the inequality exists. And if you are considering negation of any event, then we can get the probability of A naught or A dash, or we are saying negation. In this way, 1 minus P A. If I consider about a single event in a sample space S, here we can see that this is A. This is what we are considered as event A. And if I color this event A, then what I will get here is this is event A. And if you see about the things which is not related to event A, then it can be considered as this. Then this can be considered as the negation of A. The red colored ones are A. This green colored ones is for set A, and the red colors ones are for this A negation. Then we can get this equality. We know that by combining these two events, A and its negation, then we'll get the sample space. It is because these can be considered as two exhaustive, and therefore we can say that A plus A dash equals S. Now, if you get the probability of these events, then we can get it as probability of A plus probability of A dash equals to probability of S. But using the second rule of this probability based on the axiomatic approach, we can see that this value is equal to 1. Therefore, we can say that PA plus PA dash equals 1. That is why we can say that probability of this A negation is equal to 1 minus PA. That is how we are obtaining this equality for an event and its negation. And here I have included some activities exercise, and you can refer on those as well. And this is all what I need to discuss for today. And thank you all for participating with this session.